Hello learners, on behalf of Indira Gandhi National Open University, we welcome you for this video lecture session. Today's topic is Ideal Reheat Rankine Cycle. This is the 24th module of the course Thermodynamics and its applications. After listening to this video lecture, you will be able to understand the concept of ideal reheat cycle. You will be able to know the advantages of ideal reheat cycle. You will be able to compute the efficiency of reheat cycle, and also you will be able to solve the numerical related to reheat cycle. So let us begin our discussion. Before starting our main topic, that is ideal reheat cycle, let us first discuss about the Rankine cycle, and we will see that from this Rankine cycle how we can proceed for ideal reheat cycle. Rankine cycle is the simplest and an ideal cycle for vapor power cycles. Rankine cycle has 4 components and 4 thermodynamic processes. So each one of the process takes place in each component. The 4 components are shown in figure 1. Please see the schematic of Rankine cycle components and system. There are 4 main components in ideal Rankine cycle. Those components are boiler, turbine, condenser and pump. In the boiler, coal is burned and heat is evolved due to the burning of the coal inside the boiler, and that heat is being utilized for converting water into high pressure and high temperature steam. That high pressure, high temperature steam enters into the turbine, and point 1 depicts the entry point of the high pressure, high temperature steam inside the turbine. The point 2 is the exit point of the low pressure, low temperature steam coming out from the turbine, and WT is the work done by the turbine. Actually, when the high pressure, high temperature steam enters into the turbine, the shaft of the turbine rotates, and the shaft of the turbine is coupled with the shaft of the generator, which in turn producing electricity. Now at point 2, the low temperature, low pressure steam, after expansion inside the turbine, coming out from the turbine and enters into the condenser. Inside the condenser, there is heat transfer from the working fluid, that is low pressure, low temperature steam, to the cold water, which is circulating in coil for heat transfer, and Q2 is the heat given out by the low pressure, low temperature steam to the cold fluid, which is passing through the coil inside the condenser, and the point 3 is the exit point of the working fluid, which is coming out from the condenser and entering into the pump, and the pump is transferring the liquid water in the boiler. So this completes the cycle. So this diagram is the Rankine cycle components and system, and you can see that how the four components are taking part in the process. And in this case you see that Q1 is the heat input to the system, so that is considered as positive. WT is the work done by the turbine, that is also considered as positive, but Q2 is the heat loss, so Q2 is considered as negative, and WP is work done onto the system, that is considered as negative. Now for this case we have drawn the temperature entropy diagram and enthalpy entropy diagrams. So from this figure you see that point 1 is the entry point of the fluid which is in high pressure and high temperature state entering in the turbine, and point 2 is the exit point from the turbine. So work done by the turbine is H1 minus H2, and the heat given out in the condenser is H2 minus H3, and the pump work is H4 minus H3, and heat addition inside the boiler into the working fluid is H1 minus H4. And you see that the condenser and boilers are constant pressure process, and see we can also have the diagram for PV and all for the same Rankine cycle, but these two diagrams are depicting for TS diagram, and the lower one is enthalpy entropy diagram. Now this is the PV diagram. You see that point 3 is the entry point of the pump, and point 4 is the entry point of the boiler, and H1 minus H4 is the heat added to the system, and work done by the turbine is H1 minus H2, and heat loss in the condenser is H2 minus H3, and the pump work is H4 minus H3. Now the process 1 to 2 is isentropic expansion in the turbine. The process 2 to 3 is isobaric, that is constant pressure process. So the process 2 to 3 is isobaric, reversible heat rejection in the condenser. The process 3 to 4 is a reversible adiabatic compression takes place in the pump, and the process 4 to 1 is isobaric heat addition process in the boiler. To analyze and determine the efficiency of Rankine cycle by taking working fluid as water, that is 1 kg, flowing through all the components of Rankine cycle system, by observing the Rankine cycle in PV, TS and HS diagram as shown in figure 2 for calculating the efficiency of the Rankine cycle. Now let us discuss about the ideal reheat Rankine cycle. Earlier we have explained that increasing the steam pressure at inlet to the turbine and decreasing the steam pressure at exhaust will increase the thermal efficiency of vapor power cycle. In this system, the moisture problem will be encountered at the final stage of the turbine. To overcome this problem, the ideal reheat and regenerative cycle procedures will be used. In practice, reheat and regenerations both are used for improving the overall efficiency of the vapor power cycles. The reheat Rankine cycle is shown in figure 3. In this cycle, extra low pressure turbine is added. In reheat cycle, the steam is extracted from suitable point in the turbine after expansions in the high pressure turbine and is reheated with the help of flue gases in the boiler furnace. Then the reheated steam is sent to the low pressure turbine and the regular power cycle. The two turbines are used here because reheating is done at higher pressure only. The reheating can be done 2 or more stages, which will be determined by economical considerations. Advantages of reheat cycles. Weak steam causes erosion and corrosions to the blades of the turbine. Reheated steam eliminates the corrosion and erosion to the blades of the turbine. Turbine output will be increased. Eta thermal, that is the thermal efficiency, will be increased. Final dryness fraction is improved. Nozzle and blade efficiencies are increased and specific steam consumption is decreased. Now you see that this is the diagram of reheat cycle equipment. So here you see the boiler, which is generating high pressure high temperature steam, and the point 1 is the entry point of the high pressure high temperature steam in the first turbine. We call it high pressure turbine, and there is expansion of the working fluid takes place, and after that it is the steam is coming out from the high pressure turbine, and with the help of reheater again it is reheated, and after that it is entering into the low pressure turbine. Then the next subsequent processes are the same process which we have discussed for the ideal Rankine cycle process, because the low pressure low temperature steam which comes out from the low pressure turbine that passes through the condenser, and the low pressure low temperature steam will be condensed into water. After that the pump is there to send back this water in the boiler. But here we are using two turbines. One is high pressure turbine. This high pressure turbine receives the high pressure high temperature steam that is coming out from the boiler and entering into the high pressure turbine. After that, the steam which is coming out from the high pressure turbine that is being further heated with the help of reheater, and after that it is sending to the low pressure turbine, and there is further expansions of the steam and work is done also by the low pressure turbine, and after that the low pressure and low temperature steam will come out from the low pressure turbine, and the next subsequent processes are same as the ideal Rankine cycle, because the low pressure low temperature steam coming out from the low pressure turbine, it enters into the condenser in which the low pressure low temperature steam will give out the heat to the circulating cold water inside the condenser, and after that it will be leaving the condenser and entering into the pump, and this pump is pumping back to the liquid water back to the boiler, and it completes the whole cyclic process. And now you will see how we can calculate the net work done for this case. This is the TS diagram for reheat Rankine cycle. Now, one is the entry point of the high pressure, high temperature steam into the high pressure turbine, and H4S is the isentropic process for the exit of the turbine. But what is happening in between that, when it is in between some pressure, say for example for this case P3, that after the expansion in the first turbine, that is high pressure turbine, that particular point it will reach as a saturated vapor. At that point it is again reheated by the reheater up to the 0.3, and when it is reheated, after that at 0.3 it is entering into the low pressure turbine, does work, and 4S is the exit point of the fluid in the low pressure turbine, and after that it is being condensed in the condenser, and the 0.5 is the entry point of the pump, and 6x point is the exit point of the fluid in the pump. So in this case you see that the first stage, that is high pressure turbine, there is work done by the turbine that is equal to H1 minus H2S. After that it is being heated from that particular point up to the 0.3, that is the entry point of the low pressure turbine, and there is work done by the low pressure turbine, that is H3 minus H4S. So the net work done is equal to H1 minus H2S plus H3 minus H4S, in this case for the reheat Rankine cycle. But here Q1 is the heat input at the first stage in the boiler, that is equal to H1 minus H6, and of course there is heat input when it was reheated from the point 2S to 0.3. So in that case the heat input again is equal to H3 minus H2S. So net heat input is equal to H1 minus H66 plus the heat required for the reheating process. Now let us see how we can calculate the efficiency for ideal reheat cycle. Dear learners, for calculating efficiency of the reheat cycle, we will see the net work done, and we will also see what is the net heat supplied. So in this case the net work done is equal to WT minus WP, and net heat supplied is Q1. So in this particular case Q1 is the heat supplied in the boiler plus heat supplied by the reheater. So Q1 is equal to H1 minus H66 plus H3 minus H2S, and Q2 is the heat loss in the condenser, that is equal to that H4S minus H5, and we can also calculate the net work done, that is work done by the high pressure turbine plus work done by the low pressure turbine, and finally you see that efficiency is equal to net work done whole divided by heat supplied, that is Wt minus Wp whole divided by Q1. But Wt is the turbine work by the two turbines, that is high pressure turbine and the low pressure turbine. So the net work done by the two turbines is H1 minus H2S, that is for the work done by the high pressure turbine, and H3 minus H4S, that is the work done by the low pressure turbine, minus the Wp is equal to H6S minus H5, and the net heat input, that is H1 minus H6S, plus for the second case heat input in the reheater is equal to H3 minus H2S. The steam consumption rate is equal to 3600 whole divided by net work output, and with these expressions we can calculate the steam rate. Now let us discuss very interesting problem, and if you can solve these problems, or after solving this problem your concept will be very clear. So exercise 1, in a Rankine cycle steam leaves the boiler and enters the turbine at 50 bar 400 degrees centigrade. After expansion in the turbine at 5 bar, the steam is reheated to 400 degrees centigrade in a reheater and then expanded in the low pressure turbine to 10 kilopascal. Determine the cycle efficiency. Now let us see how we can solve these problems. First of all, the initial pressure and initial temperature before entering in the turbine, it is given as 50 bar and 400 degree centigrade. So this temperature and this pressure, of course this is in superheated conditions, so you can get the entropy for this particular point from the steam table. After that, expansion takes place, and at 5 bar again the steam is reheated to 400 degrees centigrade in the reheater and then expanded to the low pressure turbine to 10 kilopascal. Now let us see how we can proceed this problem. But again, for solving any problem, first you have to note down the data given for this particular problem. After that you can proceed scientifically. So this is the diagram for reheat Rankine cycle. This is known as the TS diagram, temperature entropy diagram for reheat Rankine cycle. Now you see that point 1 is the entry point of the steam in the high pressure turbine, and 2S is the exit point of the turbine, high pressure turbine. After that it is reheated from 2S to point 3 in the reheater. Again the point 3 is the entry point of the reheated steam in the low pressure turbine, and 4S is the exit point of the low pressure low temperature steam coming out from the low pressure turbine, and 4S is the entry point of the condenser, 5 is the exit point of the condenser, that is also equal to the entry point of the pump, and 6S is the exit point of the turbine. And you see that P1, P2, P3 are all given, and let us see how we can proceed for this particular problem. From steam table at pressure 50 bar and 400 degree centigrade, we can get the information for enthalpy as well as entropy from the steam table. H1 is given as 3195 kilojoule per kg, and entropy at 0.1, that is S1, is also we can get from the steam table, that is 6.6458 kilojoule per kg. At 5 bar we can get the information of the entropy at the saturated liquid line and the saturated vapor line are known. We can also calculate the SFG and HF and the HFG for the pressure 5 bar. At 5 bar 400 degrees centigrade, you can calculate the enthalpy, entropy, and also you can calculate the specific volume of the liquid at the entry point of the pump. So WP is the pump work, that is V at the entry point of the pump multiplied by P1 minus P2, that comes out to be 4.91 kilojoule per kg. So for this case, the pump work WP is equal to 4.99 kilojoule per kg. Now S2S is equal to S1. So from here we can calculate the quality of steam at the point 2S. So X2 is equal to 0.965. You can calculate H2S. After calculating H2S, you can calculate the dryness fraction at 0.4, and after that you can calculate the H4S, because at 10 bar you get all the information with regard to HF and HFG from the steam table. So H4S is equal to 2470 kilojoule per kg. Now reheat cycle efficiency is equal to eta reheat is equal to net work done by heat supplied. So net work done means the work done by the high pressure turbine, that is H1 minus H2S, the work done by the low pressure turbine, that is equal to H3 minus H4S, and WP is also known. So the net work done is equal to W high pressure turbine plus W low pressure turbine minus work done by the pump. So after putting all these values, because W high pressure turbine is nothing but H1 minus H2S, W low pressure, that is work done by the low pressure turbine, is equal to H3 minus H4S, and minus WP. WP is the work done by the pump, and that equal to H6S minus H3. So all the values are known. You can calculate the efficiency, and of course the Q1, that is H1 minus H6S, and Q reheater is H3 minus H4S. All the values are known, so just put the values in the expressions. You can calculate the efficiency of the ideal reheat cycle. For this problem, this comes out to be 0.3664 or 36.64%. Now we have concluded today's discussion. Let us very quickly summarize what we have discussed in today's lecture session. We have discussed the concept of reheat cycle. We have discussed the advantages of ideal reheat cycle. We have discussed the efficiency of reheat cycle, and finally we have done a very interesting problem related to reheat cycle, so that our concept becomes so clear, and I hope that you can solve any problems related to reheat cycle, provided you follow our instructions. First, jotting down the data given for this diagram. You have to draw the cycle diagram, especially for any problems. If you draw the TS diagram, it will be helpful. There you can calculate the work done by the turbine and work done by the palm. You can calculate the net work done and the net heat input, and you will be able to calculate the efficiency, which is defined as the net work done divided by the net heat input. Thank you very much.